Number 7, 8, and 9, we're doing predictions from the least squares regression line. So y hat equals 8.45 minus 0.27x is your least squares regression line. This value right here, the one in front of the x, is the slope of your line. You can see that this line has a negative slope. That's the slope of my line. So what they have here is my table here. The well-known psychologist, Dr. Elbod, has established what he calls his Generalized Anxiety Scale, GAS. The GAS score, which is a scale from 0 to 10, measures the general anxiety of an individual with a higher GAS score corresponding to more anxiety. Dr. Elbod's assessment of anxiety is based on a variety of measurements, both physiological and psychological. There we go. We're interested in making predictions about individual sleep behavior based on their GAS score. The bivariate data below gives the GAS score denoted by X and the number of hours of sleep last night denoted by Y. For each of the 15 adults in the study, the least squares regression line for the data has the equation y hat equals 8.45 minus 0.27x. This line, along with the scatter plot of the data, is shown below. So here they have the original data. That's the dots on my plot. Here they put in that line of best fit, that least squares regression line, and that's the equation of my line. So the first part says, fill in the blank. For these GAS scores that are greater than the mean of the GAS scores tend to be paired with sleep times that are blank than the mean of the sleep times. So when I do my means are my averages. What I do to figure out the mean is I just think about here is about the middle of my thing, here's about the middle of my thing. My x-axis, my horizontal axis, or my x scores would be the mean of my x scores, because that's the mean of my x-axis. Here would be the mean of my y scores. So we are going to figure out for the data scores that are greater than the mean of the GAS scores. The GAS scores are your x ones, and the y are your sleep times. So for these values here that are greater than the GAS scores, they tend to be, I'm going to mark all of them here. All of these on this side. Those values that are greater than my GAS score tend to be greater or less than the mean of my sleep times. Well, the mean of my sleep times is this bar right here. Do I have more dots above the bar or more dots below the bar? In this case, I have more dots that are below the bar, and so they would be less than the mean of the sleep times. So my mean of my x is going to go vertical. The mean of my y will go horizontal. So here I'm checking if I'm greater than my x, so everything on the right, where do I have more dots? Less than my y. According to the regression equation, here's my regression equation. For an increase of 1 in GAS score, there is a corresponding decrease of how many hours in sleep. We use the slope of the line to figure out what the decrease is. In this case, we see that the slope is negative 0.27, which means it decreases by 0.27 for every 1 increase in x. Number 3, from the regression equation, what is the predicted sleep time in hours when the GAS score is 3? So what we're going to do is use our regression equation, put 3 in for x and calculate that. Y hat is equal to 8.45 minus 0.27 times 3. And so I'm going to go ahead. This one says round your answer to at least 1 decimal place. So take 8.45 minus 0.27 times 3. If you round that off to 1 decimal place, you should come up with somewhere around 7.6. 7.6. So that means exactly on my line, when x is equal to 3, I would be at 7.6 on my line. Number 4, what is the observed sleep time in hours when the GAS score is 3.0? So on this one, for the observed one, you're going to find it in the table. So in my table, I want to find the data point that has a GAS score of 3. The sleep time there then is exactly 7.0. So that one I can just pull right out of the table. Number 8 then. The managers of an electric utility wishes to examine the relationship between temperature and electricity used in the utility service region during the summer months. In particular, the manager wishes to be able to predict total electricity use for a day from a maximum temperature that day. The bivariate data given below gives the maximum temperature in degrees Fahrenheit and the electricity use in thousands of kilowatt hours of electricity generated and sold for a random sample of 16 summer days. A best fit line for the equation obtained from the least squares regression is given by y hat equals 57.99 plus 2.99x. So in this case, the slope of my line is the 2.99 in front of the x, in which x denotes the maximum temperature and y denotes the electricity use. This line is shown in the figure 1 scatter plot. So in my scatter plot, x is the temperature, the electricity use is the y. So again, this first question is going to talk about the mean. So the mean would be about halfway between. The mean of x is your temperature. The mean of y about halfway between here. The mean of y is going to be your electricity use. So for the data values for electricity use that are greater than the mean, so this time I'm doing greater than the mean of the electricity use, I'm doing the values that are above that mean line. For the values that are greater than the mean of the electricity use tend to be paired with temperatures that are greater than or less than the mean. So for my temperatures here, I want to look, do I have more dots above the line, or I shouldn't say that, more dots to the right or more dots to the left, because I'm looking this way, that's where my circle goes. If I look here, I have more dots over here on the right-hand side than I do on the left-hand side. So since I have more dots on the right, I'm going greater. So when my mean is greater for my electricity, my temperature is also going to be greater in this case. Number 2, fill in the blank according to the regression equation. For the increase of 1 degree Fahrenheit in temperature, there is a corresponding, and what they want you to pick here is, are you increasing or decreasing by 2.99 thousandths of kilowatt hours in my electricity use? So I look at my slope. My slope was 2.99. It's positive. Since my slope is positive, it's going to increase, right? My line is increasing with the more electricity that I use. What is the observed electricity use in thousands of kilowatt hours when the temperature is 98.3? So for the observed one, that's where we look it up in the table. 98.3 I have to find in my table. 98.3 is the second one from the top. And the corresponding value that goes with 98.3 then is 298.0. And then the fourth question there, from my regression equation, what is the predicted electricity use in thousands of kilowatt hours when the temperature is 98.3? So now they're going to have us use the equation. Y hat equals 57.99 plus 2.99x. I'm going to substitute in 98.3 for my x. So I'm going to do 57.99 plus 2.99 times my 98.3. Just plugging that into my regression equation. Again, we're rounding our answer to at least one decimal place. So if you take 57.99 plus 2.99 times my 98.3, I should come up with 351.9. 351.9. And number 9. The Cadet is a popular model of sport utility vehicle known for its relatively high resale value. The bivariate data given below were taken from the sample of 16 cadets, each bought new 2 years ago, and each sold within the past month. For each cadet in the sample, we have listed both the mileage, X, in thousands of miles, and the cadet had on its odometer at the time it was sold, used, and the price Y in thousands of dollars at which the cadet was sold, used, with the aim of predicting the used selling price from the number of miles driven. We might examine the linear square regression line, the line of best fit, as y hat equals 41.09 minus 0.46x. This line is shown in the scatter plot of figure 1. So they're selling their used vehicle based on the mileage. What is the price that the person received? So in this case, again, fill in the blank. For these data used in the selling price that are greater than the mean of the used selling price tend to be paired with which mileages that are blank of the mean of the mileages. So again, vertical line is my X bar, my X is my mileage. Horizontal line, look for about the average or the middle. My Y bar is going to be my price. So, for the data, the used selling price that are greater than the mean, so the ones that are greater than the mean, above my line, tend to be paired with mileages that are, so I'm looking at my mileages, do I have more mileages to the left or to the right? We have more dots over here on the left side, so that means it's less than the mean of the mileages. If I were on the right, it'd be greater. On the left, it's less. Number 2 here. According to the regression equation, for an increase of 1,000 miles in cadet mileages, there's a corresponding decrease of how many thousands of dollars in the used selling price. So again, I'm looking at the slope of my line. Since my slope is negative, it is a decrease, and they tell me that in the problem. It is going to decrease by 0.46 then. So I'm using my slope to answer that question. From the regression equation, what is the predicted used selling price when the mileage is 39.2? So now I'm going to use my regression equation. Y hat equals 41.09 minus 0.46x. I am going to use 39.2 in for my x value. So I'm going to do 41.09 minus 0.46 times 39.2. Just plugging that value into my regression equation. I'm going to predict what it might be. So if I put that number in there, 41.09 minus 0.46 times 39.2, rounding to 1 decimal place, my answer would be 23.1. And number 4, they're also going to use your regression equation. So basically you're doing the exact same for number 3. From the regression equation, what is the predicted used selling price in thousands of dollars when the mileage is 21.8? So now we're going to use our regression equation, 4.09. Whoa. Stop writing on me for a minute. Doesn't want me to write. Well, let me do this. It'll write in red, but it should write. There we go. 41.09 minus 0.46 times my value here, 21.8. And so if you take the 41.09 minus 0.46 times 21.8, again, we're rounding this off to 1 decimal place. I'll try to make that look like it's in red like the rest of it. 41.09 minus 0.46 times 21.8 should give you 31.14. for my predicted value using my regression equation. So this one didn't ask you for any observed ones from the table. Both of them were predictions from my regression equation, and I just plugged my number in and solved.